In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen presented a thought experiment arguing that quantum mechanics was an incomplete theory. 30 years later, physicist John Stuart Bell set out to test their paradox using strict deductive mathematical logic. Bell published a paper in 1964 designed to formalize this philosophical debate. His goal was to construct a rigid mathematical proof to see if Einstein's intuition about the universe could actually hold up under strict mathematical scrutiny. The proof begins with a physical setup proposed by physicists David Bohm and Aharonov. We take two spin 1/2 particles formed in a singlet state, a quantum state where the total spin of the pair is 0, meaning their individual spins are perfectly anti-correlated. The particles then move freely in opposite directions through an empty void. We then place measurement apparatuses on either side of the void. Specifically, Stern-Gerlach magnets, which are devices that measure a particle's spin along a precise spatial axis. We label the arbitrary orientation of these two magnets with the unit vectors A and B. This configuration of perfectly entangled particles moving infinitely far apart creates the ideal testing ground. It allows us to examine exactly what happens when a measurement on one side of the universe appears to instantly dictate the state of a particle on the other. It requires a complete pre-existing specification of the state. Bell introduces the mathematical representation of this complete specification, the hidden variable, denoted by the parameter lambda. The thesis for the remainder of Bell's analysis is clear. We will construct a strict mathematical model of a local, predetermined universe governed by this lambda parameter and attempt to align it with the known statistical predictions of quantum mechanics. If Einstein is correct and locality holds true, the deterministic mathematical framework we are about to build must be capable of perfectly replicating every quantum mechanical correlation without a single exception. We begin by formalizing the possible measurement outcomes. The result A, measuring along vector A, and the result B, measuring along vector B, can strictly only yield a value of +1 or -1. Next, we mathematically encode the locality assumption. Outcome A is written as a function exclusively of the vector A and the hidden variable lambda. Outcome B is a function exclusively of the vector B and lambda. To find the total expectation value for the system, the average of all possible measurement outcomes weighted by their probability, we construct an integral, p, over the probability distribution of the hidden variables, rho of lambda. Notice the strict mathematical isolation within this integral. The function for A contains absolutely no reference to the setting of magnet B, and the function for B contains absolutely no reference to the setting of magnet A. We then look to the established quantum mechanical expectation value for a singlet state, which is simply negative A dot B. Equation 2 represents the classical universe. Equation 3 represents the quantum universe. For a local hidden variable theory to be valid, equation 2 must perfectly equal equation 3. Before testing that equality, Bell pauses in section 3 to acknowledge a critical caveat. There is no mathematical difficulty in building a hidden variable account if we are only looking at spin measurements on a single isolated particle. If we define lambda as a localized unit vector distributed uniformly over a hemisphere, it effortlessly predetermines the spin outcome of an isolated particle along any chosen axis. This chart shows the result of averaging over that localized lambda parameter. It perfectly reproduces the standard classical expectation values, represented here by a simple, smooth cosine function. Mathematical predetermination itself is not the problem. The math only fractures when a localized probability distribution is forced to encompass the behavior of two separate spatially entangled systems. This brings us to section 4, the core contradiction. To test the absolute limits of the classical expectation integral, Bell introduces a third arbitrary measurement axis, unit vector C. We now have 3 distinct spatial measurement choices, with arbitrary angles existing between them in 3-dimensional space. Bell sets up the logical starting point of the proof. He calculates the mathematical difference between the expectation value of measuring axes A and B minus the expectation value of measuring axes A and C. Expanding this difference using our integral relies on the normalized properties of the probability distribution rho. By factoring out the shared A function from both terms, Bell algebraically simplifies the expanded integral. Because we previously established that the individual outcomes A and B can strictly never exceed an absolute value of 1, we can convert this equation into a strict inequality. This establishes a maximum possible mathematical limit. This gives us equation 15, known today as Bell's inequality. Equation 15 defines the absolute unbreakable boundary of correlation possible in any universe governed by local realism. We execute the final test. We substitute the established quantum mechanical expectation value, negative a dot b, directly into the absolute boundary established by Bell's inequality. Bell proves the failure using a specific angular example, testing the inequality's limits with small, finite values, represented algebraically by epsilon and delta. Because epsilon cannot mathematically be arbitrarily small, the resulting equation definitively breaks. The quantum mechanical correlation definitively exceeds the strict bounds of classical probability. The deduction is complete. The quantum mechanical expectation value cannot be represented, either accurately or even approximately, by the local hidden variable integral. We step out of the pure mathematics and return to the physical measurement devices from our initial thought experiment. In his section V conclusion, Bell outlines an absolute condition. To maintain any theory where parameters predetermine individual results and still perfectly match quantum statistics, the core assumption of locality must be abandoned. Physically, this means the mechanical orientation of the first magnet dictates the behavior of the second particle, regardless of the physical distance separating them. The math forces a stark philosophical trade-off. You can have a deterministic universe with hidden variables, but you must permanently sacrifice the principle of locality to do so. The final consequence of Bell's proof is severe. If the setting of one remote device influences another to perfectly match quantum predictions, the signal between them cannot be constrained by distance. This required influence must propagate instantaneously, effectively ignoring the physical medium of space entirely. Because this requires faster-than-light coordination, any such complete theory is mathematically incompatible with Lorentz invariance, the foundational rule of relativity enforcing the speed of light as the absolute limit for information transfer. In 1935, Einstein sought to restore strict causality and locality to physics. In 1964, Bell's mathematics permanently closed that door. The EPR paradox's demand for a locally real, deterministic universe is mathematically dead. Quantum mechanics, with all its inherent non-locality, remains the victor.